welcome everyone. The topic of the webinar today is going to be survey design, and if you remember, I think everybody probably attended the webinar that we gave a few weeks ago on microseismic geomechanics essentials, and one of the key pieces I feel in a successful microseismic project to follow a prescribed workflow is the survey design element. So before collecting microseismic data, to look at potential monitoring array configurations, do some numerical testing to evaluate those and maybe rank different options to pick the one that's going to give the best expectation or the best microseismic data for given project objectives. So having said all that, the webinar this morning is going to be given by Jun-Wei Huang. Jun-Wei is a geophysicist working in Toronto for IMaGE, and the webinar is going to be a repeat of a keynote presentation that Jun-Wei gave a few weeks ago at a SEG workshop on microseismic in Hefei, China. I guess with that, I'll thank Jun-Wei for agreeing to repeat his keynote, and I'll pass it over to Jun-Wei.
Okay, thanks, Sean. So welcome everyone to this second webinar of our webinar series, Mastering Microseismic and Geomechanics. So if you attended the previous webinar, you should remember Sean gave a very good overview of microseismic and geomechanics techniques, and those techniques are valuable for the multiple applications, and this is the slides I stole from the previous presentation. And if you missed Sean's presentation, you can always go to our webpage, and we have that recorded, and you can watch the previous presentation. So Sean covers a lot of topics in microseismic and geomechanics, and the following series of webinars is to elaborate on those important topics and to share with you our experience in the past, and hopefully as the industry renewed interest in microseismic and geomechanics, we can all approach the problem in an appropriate way, and we can grow the technology together. So the following webinar will be covered the entire workflow of microseismics and the geomechanics as well. And this webinar will focus on the survey design, the phase that before your project starts, you want to maximize your investment in the monitoring, so you can understand how the geometry will impact your data quality. In the following webinar after mine, there will be a series of webinars focus on different topics. 1 or 2 will be in the data processing and advanced data processing, and a few webinars will focus on the interpretation and particularly the quality control to understand the biases in the data, so we don't over-interpret our results in terms of the rock response. And then those information will be feedback in IMaGE. What we do is calibrate a numerical model based on the observation from microseismic, and we can use the numerical model to predict a rock response in a different setting, and that can help us to do a better survey design in the next for the next project. So that's the entire workflow, and we have webinars elaborate on different topics, and this one can be focused on the survey design, the so-called the foresight before your project begins. So Sean mentioned this is a keynote I gave a few weeks ago. So the title was Optimal Microseismic Network Design for Induced Seismicity. So I just want to share basically 3 steps to design a cost-effective network. So we have a very interesting project. The interesting part is we did the survey design, and then we went ahead and acquired the data and processed the data. The data quality is consistent with the prediction that we made in the design phase. So we think a few things that we did right in this project, and that's what we're going to focus in this presentation. So first of all, a little bit background about induced seismicity and why it's important. So when we talk about induced seismicity, we mean the anthropogenic earthquakes, the earthquakes that are human being activities are responsible for instead of plate tectonics, and it's a concern across multiple fields. So for instance, the petroleum industry is looking at induced seismicity because you inject the fluid, you're going to cause earthquakes, and although you have done millions of injections, you don't need many big earthquakes. One or two going to cause the society to panic, and will lose the so-called social license to continue benefit from the hydraulic fracturing technique. The seismologist is also interested in the induced seismicity. They want to know how it occurs and how to mitigate the hazard to understand the mechanisms behind the induced earthquakes. And also the insurance companies are also looking at the induced seismicity. They are probably thinking increasing your premiums if some certain activities is going on in your neighborhood. And those activities are not really only constrained to hydraulic fracturing. It could be many other activities such as CO2 sequestration. You inject the supercritical CO2 and that may break the rock and earthquake. You build a dam and you control the water level in the dams, and that could also trigger an earthquake. Geothermal is another case that you inject the fluid, and that's going to cause earthquake hazard as well. Same for mining-induced earthquake. It has nothing to do with fluid injection. It's just you take some mass away or you put some mass on top of the existing situation. The change of the stress gonna diffuse away, and that gonna potentially cause an earthquake in your mining site. So that's why a lot of government around the globe enforce the monitoring of induced seismicity. You have to comply with the local laws so that you can perform those activities. So this will be the outline of this presentation. Our case studies from the Northeastern British Columbia, Canada, and the three takeaway messages or the three critical steps that we think are useful is first, maximize your coverage with minimum magnitude sensitivity, and I'll show you how to do that later, and also evaluate the location uncertainty using a multi-Carlo simulation, and then more importantly calibrate the network performance using a baseline noise survey. For before your injection, before any operations, you acquire a baseline noise to understand the different scenarios in that in your specific field. And then I'll show some monitoring results. It's still kind of under review by the company, so I can only show you a limited results from that. And we went one step ahead and look at what if we didn't use surface array. So this is a surface monitoring project. What if we use a single borehole or increase the density of the survey of the surface survey? What are we going to get and what are we going to lose in the different situation? And then I'll draw the conclusions. Basically, I want to say there's no the best network. There's only the one that fits your engineer purpose. And again, you can go back and use this 3 steps to evaluate if a given network is going to satisfy your engineer purpose. So here's our case study, Northeast British Columbia province right here. This is the national map of Canada. And I think in late 2006, unconventional oil and gas activities occurs in this region, and thousands of wells has been drilled, and most of them are horizontal drilling with hydraulic fracturing and also long-term wastewater disposals. So back then, I think there's only 2 broadband stations like these black triangles in this region. But even that, people observe a very strong correlation between the fluid injection and the earthquake level. So in 2013, a research consortium was formed, and the first thing they did is to, well, the purpose is to understand the induced seismicity in this region, and the first thing they did is they increased the number of stations from 2 to 8, so they add a multiple broadband stations, and the data are publicly available, waveform catalog. So what I did is I downloaded the catalog from 2013 and all the way till the day before our project. So I plot them using our software. So you can see most of them are small events with a few large events, could be as high as 4.5 magnitude. And those large events are causing damages to the near epicenter areas. So if you believe that follows a Gutenberg relationship, then I can plot the number of events as a function of magnitude, and I can estimate the slope. The slope gives me the b-value around 1.1, and you see the turning points here, like the turning corners. The events weaker than that is not well represented in the catalog because of the limit of your network, and events above this level are captured in this catalog. So we can consider this as the magnitude of completeness. It's kind of a parameters that evaluate the sensitivity of your network. So for this one, I think it's around 1.7, and before it's about 2 point something. So it's kind of 1 magnitude more sensitive compared to the previous one. And so the government now, it's like they install a traffic light, a camera, and they can capture anyone who not obey, not compliant with the local traffic light system. So here's our project here. We have some general engineer objective. The first objective is this is a horizontal multilateral hydraulic fracturing project. So the well pad is here and it's drilling horizontally along this direction. So the first purpose of this is, of course, comply with the local regulators. And the second purpose is also try to understand how effective the injection was, and if we have done a good job of hydraulic fracturing the reservoir, and maybe correlate the production with the injection in the future, so we can evaluate the investment. So that's two a primary engineer objective, and that leads to some general requirement. For example, if we're doing the surface monitoring, the distance between the stations has to be empirically 1 to 1.5 times the distance, the depth that we're looking at. The second general requirement is logistically feasible. We should be able to access this land. Remember, the insurance company are looking at these issues, so maybe we will have landowners that doesn't like those activities in the first place. So it has to be logistically feasible, and also low ambient noise. So it should be away from the culture noise. So those general requirements lead to a few specific requirements for this project. We are looking at the injection point 2.5 kilometers from the surface. So that means the distance should be around 4 kilometers away. So you see here, these two stations are larger than 4, but along this direction, the distance is less than, it's about 3.8 kilometers. And then it should be as close as possible to facilities so we can maintain the stations. And also it should be as far as possible from facilities so we can minimize the noise. So you see those requirements are kind of self-conflicting, and to balance those requirements doesn't give us much options, and we end up with this geometries here. S1 is the one closest to the well pad. It is the most noisy one. You can hear engines and the trucks going by. S5 is the most quiet one. It's because it's close to the end of a local road and there's no exit. So not much go-through traffic is there. S2 and S4 are just in the middle. So the first step is now we have the acquisition geometries. Can we evaluate how sensitive of this network? So we use the lowest moment magnitude that can generate a seismic signal above the noise floor. So this is the equation, just specify exactly how we correlate a moment magnitude to a signal amplitude at a station. So I'll skip the details of the equation, but I want to point out it correlates the radiation coefficient, the Q value, and the corner frequency with the displacement, the velocity displacement at the station. So if you know your source may slide along the specific directions, you can build in a specific radiation pattern in this equation. But in this case, we assume we don't know what's the preferred orientation for the rock breaking. So we use a constant values here. And then we have a background noise. The algorithm works like this. For every grid point in space, we increase the magnitude from low to high and then calculate the signals at any given stations. So for instance, the signal below 1, then you got signals that below the noise. You cannot detect signals like this. So you keep increasing the magnitude till you reach a level that you're satisfied. We use 2.0 in this case to make sure we have a reliable detection of signals. If you use 1.0, some processors, it's kind of debatable. Some processors may skip that signal and some processors may consider that is a signal. So we use 2.0 to have a reliable detection of the events. And just draw your attention to the background root mean square noise. It's not static. It's a function of time. So it's just as dynamic as your signal. So we'll come back to these issues later. So if we do that calculation on a 2D plan that is at the depth of the treatment, that's 2.5 kilometers depth, and we can calculate the minimum magnitude on every single grid points. So you see a pattern like this. It's required all 4 stations can detect the signal. So you can see this blue greenish areas kind of mimicking the rectangular shape on the surface. That's your coverage of this network, and this is the region that you're most interested in, and it has a comprehensive coverage in a place. So in other words, you don't see a place that's more sensitive compared to another locations. So there, overall, it's a good coverage in this project. So that's the minimum magnitude. The next step is to look at the location uncertainties for this network geometry. And there are many things that contribute to the locations, because we know we need the time, we need the velocity, and if we are doing a borehole monitoring, we need the source vector to locate the events. And all those parameters has errors, and those errors will be reflected in terms of the location. So how does the location uncertainty looks like if we have different level of uncertainties in those parameters? The major contribution to the arrival time uncertainty is actually the phase identification. So for instance, we have arrivals here, and different processors may pick different phases as the first P wave arrival. Some of them may consider I'm picking the first arrival anyhow, so I'm going to pick, I see some energy here, so I'm going to pick this one. Some of them consider, well, this is head wave, so I'm picking the body wave, so I'm going to pick this one, and someone consider this is your real body wave. So if I increase the amplitude, they may all change their mind. So this is kind of demonstrate the phase identification and uncertainty is difficult to quantify, and it will introduce the systematic errors if you don't pick the right phase. And we have a different techniques in the following webinar we'll cover is we can use the synthetic data to help us that pick the right phase when we are doing the quality control step. The other contribution to arrival time is the picking accuracy. So usually, if the sampling interval is a normal sampling interval, empirically you can use 2 to 5 times of the sampling interval as your picking accuracy. The second uncertainty is the velocity uncertainty. So I use a picture from Sean's book to demonstrate the ideas. So each layer will have errors. So for instance, we have a vertical borehole and we have 5 known short positions. By only change the velocity, P wave and shear wave in the same way, we are actually pushing and pulling away the events. And this is just for one layer. If we change the layer on the top 2 and change them in the same way, you're going to change the positions as well. And that uncertainty is different at different location. So you can imagine we have multiple layers, and each layer will have error independent from the other velocities and from each other, from different layers. How does that affect your location uncertainty? We propose this Monte Carlo simulation. I think most vendors provide such a tool. So if you do have that, we would recommend you use that and try to get an error ellipsoid around your positions to evaluate the location uncertainties based on the velocity. The other one is source vector. We didn't use it in our project because we're using the surface monitoring, but if you're doing a borehole monitoring, and that's basically the error you're going to have. If you have a particle motion come 45-degree angle, without error, you perfectly get the direction where the energy comes from. But if you just introduce random errors to the synthetic data and you try to estimate a linear trend from your data, you probably get this orange direction. And that's, in this case, almost 5 degree or 10 degrees differences from the true location. So that's another uncertainties that we can think of. In the surface monitoring, we don't have that. Problem. So this is the location uncertainty I did using the Monte Carlo simulation. I picked 3 representative locations. So we have A and B close to the top and bottom edge, and we have C right on top of the wellbore. So kind of a representative 3 locations, and then start from simple. I just assume there's P wave error and a shear wave error, and this error is just 1 times standard deviation, and it's a Gaussian error, so you can assume it's 3 times this error is 99% of the perturbation will be within that range. So it's relatively a large peaking errors, and assume the velocity is well calibrated, then we can estimate the uncertainties, epicentral uncertainties, about 80 along east and the west, 100 along north and south, and that's because we have a relatively large distance along this way, and that's, I guess that explains the differences here. But the dominant uncertainty is the vertical depth. It's 200 meters, and that's assuming the velocity is correct. Now if we add 5% uncertainty to the velocity, so that means if your velocity for that layer is 5,000, and then you will get 250 meters errors for that layer. And you can see it's almost doubles the vertical errors, 300 or almost 400 meters. So the byproduct from this exercise is that if you're using a surface monitoring and you see your fractures grow up or down by 400 or even 200 to 400 meters, you cannot explain that as the fractures growing that high, because as you see here, it's still within the location uncertainty. So to understand the vertical growth, you probably want to switch to a borehole monitoring. Then the third step is to calibrate the network. So we understand the network from the coverage, from the location uncertainty. Then we did is we acquired some baseline survey before anything begins. And there are basically 2 ways. So there are many contributions to the noise. For example, the fluid injection will cause noise. The engine on the surface and local traffic will increase. So there are many noise sources that you need to consider for different cases. So we have 2 different ways to calculate. One is simple. If you're doing real-time processing, what you can do is just take a chunk of data, for example, an hour, and then you can draw a line and you say, well, 50% of the signals is at this level, or noise is at this level, so I can consider within this time period my noise level is about 200 nanometers per second. This is a root mean square of a waveform. So the more sophisticated way is you can still take a time chunk, an hour, a day, or a few days, and then you chop them into small time windows. And for each time window, you do a FFT and estimate the power spectral density function for each discrete frequency. And for each time window, you estimate a group of numbers for different frequencies. And for a single frequency, you will end up have multiple time windows. So could be 10,000 time windows. You will have 10,000 measurements for each frequency. Then what you can do is to plot the histogram or estimate the probability of that power spectral density function, and you plot that as a function of frequency. So these 2 figures are the probability power spectral density function as a function of period. So it's 1 over frequency, and that's the frequency we're interested in. And it's from station 5, so the most quiet one. So 7 days before the operation begins, it's almost 10 to minus 7, so translate to 100 on 200 nanometers per second in a time domain. And 1 to 3 days before the operation, I think the engineers start doing the preparation, and the noise start to increase in this region, and that translates to about 1,000 nanometers per second, the high end. And you can also do that during the operation, and of course that noise is even higher, and some of them are probably the contribution of your induced seismicity there. So that's the 2 ways to estimate the noise. And what we did is now I use the magnitude threshold to estimate the minimum detectable magnitude in this region. So instead of using 4 stations, now I use 3. So I have less requirement, less demand on the network. So you can see start to have this diamond shape compared to the previous one. We use 4 stations. And I can only show you one piece of data here. Is that's what we recorded, the minimum events after a alter processing. So the minimum events is 0.54. And you can see here, this is the magnitude threshold. For different noise background, the pattern is not going to change. It's going to change the values corresponding to different color. So if the noise level is 200 meters per second, then we have a 0.36 minimum detectable magnitude. 400 will increase that level, and for 100, 1,000, the minimum detectable magnitude will goes up to 0.9. So now we have different scenarios, and we can correlate with our data. So I think I mentioned this is older processing results. So you can imagine if we go back and do some manual processing, then we should be able to push this value even down. So that means our noise level for this site is probably within this region, 200 to 400 nanometers per second. And you can also plot the waveform. That's what I said. It's the older peaking requires relatively high quality of signal. So you can see the signal to noise ratio is, I think it's almost 3 or 4 in this case. The data catalog is still incomplete because it's only older processing, and we can plot the number of events with moment magnitude and estimate the b-value. The b-value is almost close to 1, similar to the one from the national network. And we can also try to estimate the magnitude of completeness based on this. And you can see it's probably around 1. And compared to the one that from the national network, it's more sensitive. So that means we're using this network, we're able to traffic light systems enforced in that place. So below 2, it's fine. 2 to 5, you may need to change your operation. If it's above 4, you need to stop your operation. So the next step is we start looking at a different acquisition geometries. So what if we use a different surveys, for example, using a conventional 12 geophones? What would be the data looks like? So I did this 2 exercise. One is a single borehole here, and one is a 10 by 10 grid surfaces. So I increase the density of the surface survey. Noise flow, of course, will be different because we're now closer to this to the operation and far away from the noise source. And I only require 3 stations to be able to pick up the signals. So you can see this is the borehole, that's the treatment well, and the minimum detectable magnitude goes down to -2. And if you can see this, probably the region that we're most interested in, he has a acquisition footprint that is moving further away. You will be able to detect weaker events. If we're using a 10 by 10 grid locations, so in total we have 1,000 geophones on the surface or broadband stations on the surface, and it has a comprehensive coverage. It doesn't have acquisition footprints in the radial direction like the borehole. The minimum detectable magnitude now is much lower compared to the one that we have, and that's what you get by increasing the density. And I'll show you later what else benefits we can get by using a geometry like this. So what does it mean? It means if we're using a borehole, we're looking at -2, and that corresponding to an upper limit of the frequency. It's about 1,000 hertz. And if we're doing the surface survey, then we're probably looking at the events that's up to 100 hertz. And I do have a reservoir engineer clients that asking their geophysics group for a -2 events when they're using a surface geophones up to 100 hertz. So that means they either have to choose a different geophones or they change their expectations. So if you're expecting -1, then you don't expect that, or you change your geophone broadband to be able to cover a -1 events from surface. So if we have data that are quiet, it will look like this. Close to the events, we have small events. Further away, we'll see less. And compared with the surface, we'll only be able to recover a strong events. So compared with this one, it's much more sensitive compared with the 4 stations one. Now that's the magnitude sensitivity. We can also look at the different arrays from the uncertainty analysis. So this is the borehole uncertainty analysis. I didn't include the source vector. Just want to show you without that, these events can be located anywhere along this curve. So we need to include a source vector. Let's say we have a 10-degree source vector uncertainties, and we have velocity, travel time error, velocity error. And I just want to point out this spreading here. Close to the observation borehole, the spreading is less, and further away, we have a larger spreadings. And we know the true location is actually in the middle of the cloud. So what does that mean? If we observe using a single borehole and see a spreading like this from this acquisition geometry, we cannot interpret that spreading as the complexity of the network. It's very likely you're interpreting the uncertainties as part of your fracture, and that's not a correct interpretation. Now for the surface, we can also do something similar. What we got here is we use the same uncertainty and assume the velocity well calibrated. What we got is a very high accuracy on the location. As you remember, the vertical one, if you're using 4 stations, is 200, and now it becomes much less. It's about 8 meters in this case. Now what we lose is the robustness on velocity. So if we assume the velocity is not that well calibrated, 1% error, then the epicentral uncertainties remains almost the same, but the vertical uncertainties increases to 400 meters. So the gain you got here is higher accuracy if you can get a very good velocity model. The loss here is it becomes very sensitive to your velocities, and if you have velocity error, you expect a relatively large uncertainties on the vertical direction. So compared to that, it's almost like a four station case. So that's my conclusion here. We have a microseismic network design. We predict the performance, and then we look at the data, and the observation looks very similar. So we think the following 3 steps are critical that makes our prediction consistent with the observation. One is magnitude threshold to evaluate the coverage, multi-color analysis to understand the biases, and also try to get a multiple noise scenarios by calibrating with the baseline survey. And this is a very important quality control step, and just want to emphasize the quality control is not only important before your project, it's also important when you do the data processing, and also after the data processing you want to evaluate your quality of data. You can also use a survey design. So everything that the figures that I produced, they're using an Insight as well as Insight design. So if you're interested in any of those functions, you're welcome to contact us, and we can show you more of those functions. So that's basically my webinar. So the next one, as I showed you, is moving on from the survey design to data processing. So next one will be the data harvesting and processing, and try to give you a workflow of how we can get from continuous raw data to start deliver results. It will be in July. So hope you can stay for that one. Right, thanks for your attention. If there's any questions, I'll be happy to answer.